Hello, my name is Jared Skeens and welcome to the Zoom room. Today we would like to cover mechanics, momentum, part 1, collisions and coalescence. Now momentum is a new unit in the Cambridge Mechanics syllabus and just starting with the new syllabus of 2020. So this might be new to some of you if you're teaching the Cambridge. And there's only one formula that we really need to keep track of. That's momentum equals mass times velocity. Momentum equals mass times velocity. And there is a conservation of momentum. So the two words that we want to keep track of are collisions and coalescence. Collisions means that you have two objects that collide, and after the collision, they continue on as separate objects. In coalescence, you have two objects that collide, but then continue on as one singular object. So they kind of merge together into one, and they use the word coalescence. So because there is a conservation of momentum, then the momentum of the objects before a collision will be equal to the momentum of the objects after a collision. So we can use this to help solve some problems. Again, remember that mechanics is cumulative, so there are other things that we've already learned that might come into these question types as well. So let's take a look at our first question here. And it says particles P of mass m kilograms and Q of mass 0.2 kilograms are free to move on a smooth horizontal plane. P is projected at a speed of 2 meters per second toward Q, which is stationary. After the collision, P and Q move in opposite directions with speeds of 0.5 meters per second and 1 meter per second respectively. Find M. So we need to find the mass of particle P. So let's go back to the board. Remember, as always with mechanics, you want to draw a good diagram, and this diagram isn't complicated or anything, but you want to have a diagram so that you can put your information together. So we have a smooth horizontal plane. We have particle P, which is said to have been projected at 2 meters per second and has a mass of m kilograms. We're solving for the m. And particle Q is stationary on this horizontal plane. So stationary means it's at rest or zero velocity. And it has a mass of 0.2. This is our situation before the collision. After the collision, it says that they are going in opposite directions. Now, direction doesn't really have anything to do with momentum per se, but the fact that it's going in the opposite direction with velocity, it changes the sign of the velocity. So it will make a difference in your calculation. It doesn't affect the concept of momentum, but you need to realize that velocity is now going back towards the origin instead of continuing on away from the origin. So that part does make a difference. So we have a negative 0.5 meters per second because it's now going the other direction. And Q continues or starts to go in forward with a 1 meter per second. So basically what we want to do is just follow our formula here. Momentum is mass times velocity. So our mass for particle P is m times 2 plus our mass 0.2 times 0 equals, here we have a mass m with a negative 0.5 plus we have 0.2 times 1. Okay, so here we have 2m plus 0.2 equals a negative 0.5m plus 0.2. add the 0.5 to the other side. 2.5 m, oh sorry, this one is 0. 0.2 times 0 equals now 0.2 because we added the 0.5 to the other side, plus 0.5 m and plus 0.5 m. Okay, so now we divide by 2.5, divide by 2.5, and m will equal 0.08 kg, because this is mass. So that is the mass of particle P. So that one was pretty easy, not too bad. Conservation means the before and after are equal. You just add up the sums of masses and velocities and solve for the missing variable. Now let's look at what happens when it gets a little bit more complicated. Okay, let's look at the second problem that we have here. It says small smooth spheres, A and B, of equal radii and masses 4 kilograms and 2 kilograms respectively, lie on a smooth horizontal plane. Initially, B is at rest and A is moving towards B with speed of 10 meters per second. After the spheres collide, A continues to move in the same direction, but with half the speed of B. Find the speed of B after the collision. So let's again start with our diagram. So here we have, I have 3 objects because our question is going to continue. Right now we have object A and object B. Object A is 4 kilograms at 10 meters per second. Object B is at rest, 0 meters per second, and has mass of 2 kilograms. These two collide, and then after says that A is half the velocity of B. So we'll have half the velocity of B, and then of course B will have the velocity of B. So let's go ahead and follow our formula for that. So we have mass 4 times 10 plus 2 times 0 equals 4 times half B, half velocity of B, plus 2 times the velocity of B. Notice we only have one variable, so as we work this out, we have 40, that's 0, equals 2 velocity of B, plus over here we have also 2 the velocity of B. So that gives us 40 equals 4 times the velocity of B. And so our velocity of B equals 10 meters per second. So now we have we can call this 10 and half B. So this is now 5. Okay. Now let's look at the next part of the question. Says a third small smooth sphere C of mass 1 kilogram, same radii as A and B, is at rest on the plane. B now collides directly with C. After this collision, B continues to move in the same direction, but with 1/3 the speed of C. Show that there is another collision between A and B. Show that there's another collision between A and B. Okay, we got one more after that. We'll come back and look at that third part later. So now this one becomes our before, and we want to see what happens with the after. Okay, so here we have now B, which is now 10, so 2 times 10, so it's mass times its velocity plus mass times velocity, 1 times 0, now equals 2 times, and it says that B is now 1/3 of the velocity of C. So 1/3 velocity of C plus 1 times the velocity of C. So now we have 1/3 velocity of C, and this one is the velocity of C. So this will be the after part here. So now we have 20 equals 2/3 velocity of C plus 1 velocity of C. So that's 20 equals 5/3 velocity of C. 2/3 plus 1 is 5/3. And so our velocity of C now is 12 meters per second. So that's this one. This one was this one. And so this is now 12. And this is 1/3 of that, which is 4. Well, notice it says show that A collides with B again. Well, notice the velocity of A is 5. After the second collision, the velocity of B drops down to 4. They're going in the same direction. So what we want to say here is the velocity of A is greater than the velocity of B. Therefore, they will collide again for that part. Okay. So now that we have that, let's go on and look at the third part of the question. Third part of the question says A and B coalesce during this collision. A and B coalesce, that is the second time A collides with B. Find the total loss of kinetic energy in the system due to the 3 collisions. Okay. Well, let me take a moment to give us some room so we can work this problem. Okay, I've cleared some space. I've also added a little bit of detail here to the board. So our particle A is still continuing on at 5. We showed in the last part that because B is now dropped to 4 and A is going 5, which is faster, it's going to run into B and collide a second time. So this one here was the first collision between A and B. Then this is the collision between B and C. And now there's going to be another collision between A and B again. This time it says that when A and B coalesce, when they collide the second time, they will coalesce. So that means that these two will become one and will have one velocity for that one object. So that's what we need to figure out here, is what is the velocity after they have coalesced. Then we can work on the loss of kinetic energy in this entire problem. So what we have here is our before. So we have 4 mass times velocity plus 2 times 4 equals, they have coalesced, so that means we add them together. 4 plus 2 is the mass times V, which is our unknown velocity after the collision. So here we get 20 plus 8 equals 6V. So now we have 28 equals 6V. And our velocity after the collision now comes out to be 4.67 meters. 4 4.67 meters per second. Okay. So now we have all of our velocities on here. Now the question says, what is the total loss of kinetic energy? Well, kinetic energy, actually this energy part is a unit we haven't covered yet. So you might want to look ahead at the next unit, which is work, energy, and power. And you might want to watch some of those videos to learn about kinetic energy. But we're going to go ahead, because we're solving these momentum questions, we're going to go ahead and solve this part right now in this video. And you, like I said, you might have to look forward to the energy unit and then come back for it to make sense. But the kinetic energy is 1/2 mass times volume squared. That's the formula for kinetic energy that we study in the last unit of mechanics. And so if we look at our starting point, this has 0. That's no kinetic energy here. No kinetic energy. So all of the kinetic energy is with part A. So our kinetic energy for this beginning of the system here is 1/2 mass is 4 times 10 squared. Well, 10 squared is 100, half of 4 is 2, 2 times 100 is 200 joules. Energy is in joules. So the total kinetic energy at the beginning of our system is 200 joules of kinetic energy. Now what we want to do is see what has happened to that energy throughout these collisions and this coalescence. So when we get to the end, we still have, don't forget, our particle C is still in motion here. So we don't want to forget particle C. So this now is what is coming out of the end of all of these collisions. A coalesced particle traveling at 4.67 meters per second and particle C traveling at 12 meters per second. So let's look at particle AB. Kinetic energy of AB equals 1/2. The mass is now 6 because it coalesced, and the velocity 4.67. I'm just going to put 4.66 repeating so that we don't lose a significant digit there. And when we do this on our calculator, we get 1/2, so 3 times 4.666666 gives us 14. Oh, sorry, I need to square this. Don't forget the squared. Need to go back and square that number. Equals 65.3 joules. 65.3 repeating joules. That's for our coalesced particle. That's how much kinetic energy is in this coalesced AB particle. Now we want to see how much kinetic energy is in our particle C. So 1/2, mass is 1, and speed is 12, again velocity squared. So that's 144 divided by 2 is 72 joules. So our total kinetic loss of energy, our loss of kinetic energy equals what we started with at the beginning, 200, minus the sum of what we have here. So 65.3 plus 72. And when we work this out, we get a total of 62.7 joules. And again, this is a loss in our kinetic energy of 62.7 joules. So again, the energy part will actually be taught in the last unit, but again, mechanics is cumulative, so it mixes all the units together, and momentum equals mass times velocity is our important part. We have one more question that we want to look at, so let me set up for that one. Okay, let's read our last problem here. Says a particle P of mass 0.3 kilograms lying on a smooth plane inclined at 30 degrees to the horizontal is released from rest. P slides down the plane for a distance of 2.5 meters and then reaches a horizontal plane. There is no change in speed when P reaches the horizontal plane. A particle Q of mass 0.2 kilogram lies at rest on the horizontal plane 1.5 meters from the end of the inclined plane. Shows a diagram. P collides directly with Q. It is given that the horizontal plane is smooth and that after the collision, P continues moving in the same direction with a speed of 2 meters per second. So I'm just going to put that over here. And we have our distances of 1.5 meters, and we have also 2.5 meters for that one. Okay, let's go back to our board. I've drawn particle P is at rest or released from rest, slides down the smooth plane. So what we want to do is calculate the velocity when it gets to the bottom. It's then going to continue at the same velocity over this smooth horizontal surface because there's no friction, no resistance. So it will continue at the same velocity. And then it will collide with Q. Q then will continue forward with a velocity of 2 meters per second. So let's just check again really quick. Our question is find the speed of Q. Oh, P continues on with a speed of 2 afterwards. So we want to find the velocity of Q. P will have, our particle P will have the velocity of 2. So I'll just put that there. Okay. So what we want to do is first thing we want to find acceleration. The acceleration so that we can then find the velocity when it reaches the bottom of this inclined plane. But to find acceleration, we need to resolve our forces. So here, this has gravity of 0.3. 0.3 times 10 is 30 newtons. So we want to resolve that perpendicular and parallel to this. So this one will be 30 sine of, this is 3 newtons. 0.3 times 10 is 3 newtons, not 30. And this one, so is 3 sine of 30 degrees. Don't forget that this angle is the same as that one in there. Sine of 30 is 1/2. 1/2 of 3 is then 1.5 newtons. So the only force acting on this is the force resolved from gravity parallel to the direction of our inclined plane. So again, we use Newton's second law, mass times gravity, 0.3 times acceleration equals the resultant force, which there's only one, and that was our 3 sine 30, which is 1.5. So divide both sides by 0.3, and our acceleration is 5 meters per second squared. So that's our acceleration. Now we need to calculate velocity. And for velocity, we're going to use one of our Suva equations. So that goes all the way back to the first unit. So we want v squared, our final velocity, equals our initial velocity plus 2a, which we just figured out, s, which we have the distance, 2.5. So this gives us v squared equals 25. So our velocity is 5 meters per second. So right here we have a 5 meters per second. Now this is going to continue because this is a smooth plane. It's going to continue at this speed all the way until it collides with particle Q. Then after the collision, they continue on their way. P now is going 2 meters per second, and we want to solve for the velocity of Q. So this is where our momentum comes in. So our momentum is, again, mass, 0.3, times velocity, 5. This is the before, and this is the after. So plus 0.2 times 0 equals 0.3 times 2 and 0.2 v, the velocity that we're solving for. So here we get 1.5 equals 0.6 plus 0.2 v. Subtract 0.6 from both sides. So 0.9 equals 0.2 v. Divide both sides by 0.2. And our new velocity for particle P is now 4.5 meters per second. So this is 4.5. Okay, so that's how that one works. So now it's adding in a little bit of that previous material that we've already learned in mechanics. Now let's go look at the second part of the question. It says it is given instead that the horizontal plane is rough. Okay, so now we have friction involved. And when P and Q collide, they coalesce and move with the speed of 1.2 meters per second. So now we're going to have a PQ is a coalesce with a 1.2 meters per second velocity. Find the coefficient of friction between P and the horizontal plane. So let's go back to our board here. I've added now another situation. We need to find several things. We need to find the velocity of P as it reaches Q. Now that we have a rough surface, that's going to slow down our velocity. We also have a coalescence. P and Q become one object, and the speed is 1.2. So what we're doing is we're looking for the mu, the coefficient of friction. And so let's work this problem backwards. We have the answer to the end, so let's work back toward that friction part of the formula. So if we work backwards, let's start with our coalescence. So the mass would be 0.3 plus 0.2 times the velocity equals the velocities of the particles before they collided. So particle P has a mass of 0.3 times its velocity, which we don't know, plus Q has 0.2, and it has a 0 velocity before the collision. So when we get this, we have 0.5 times 1.2 equals 0.3 v. Now that we have that, now we have 0.6 equals 0.3 v. And our V now is divide by 0.3, divide by 0.3. Our velocity is now 2 meters per second. So what that means is with this rough plane, particle Q gets over here just before it collides with a velocity of 2. So it has slowed down some. So let's find, now that we've got that part, now let's work backwards again and find the acceleration. Kind of like what we did over here, but now we're working backwards. So let's find our acceleration. So we have our v squared is final velocity is 2. Our initial velocity is 5 plus 2a. We don't know the acceleration. S is 1.5. So this is our SUVA, one of our SUVA equations. So we get 4 equals 25 plus 3a. So this is a negative 21 equals 3a. Divide by 3, divide by 3, a equals a negative 7 meters per second squared. Now, the negative on the acceleration simply means it's decelerating. So it's slowing down, which makes sense. It went from 5 meters per second to 2 meters per second. So acceleration would mean speeding up. Deceleration, designated by the negative, means slowing down. Now we can use our net force and Newton's second law formula. So to do that, we need to resolve our force. Here we have 0.3 again, times 10 is 3 newtons. And our normal contact force will be 3 newtons the other way. And this is going to create a friction that will cause it to slow down. So our net force is mass times acceleration, and our acceleration is our negative 7 equals our resultant force, and there's only one force to resolve. So our resultant force is our friction, and friction is mu times the normal contact force. Well, the normal contact force is a 3 pushing up against the 3 newtons of gravity. So we have 3. So that gives us a negative 2.1 equals 3 mu. Divide by 3, divide by 3. And actually, we don't need the negative. We just need the force magnitude. And we divide by 3. So our mu, our coefficient of friction, is equal to 0.7. Okay? So we don't really need the negative on our 2.1. We're looking at it as an absolute value magnitude, and so that we can solve for the mu, the coefficient of friction. In other words, the direction of the force doesn't really matter. Your coefficient of friction is the same in either direction. Coefficient of friction has to do with the surfaces sliding over each other. So here we're able to find mu, which was the second part of our question. So that concludes our video on momentum, our new content for this new syllabus for 2020. Again, as always, thank you for watching, and look forward to seeing you when we get to the next unit.